Hello everyone. So the next topic is called exact equations. And these are a special type of differential equations um, of the following. I'm not going to show you the form yet um, because I need to review something first. And during the review, you can actually see where these exact equations come from. Let me say a quick review of implicit differentiation. Okay, so what is that? So that is, if you have a function f, say, that depends on x and y, then you can find its derivative, where with respect to x, for instance, if you think of y as a function in x. Okay, so let me start with reviewing this particular thing first. Okay, so let's take an example here. Suppose I have say x cubed y to the fourth plus cosine y plus x e to the y. Okay, that's an expression that we can have. So let's take the derivative with respect to x of this function. This is implicit differentiation. And then that was something in Calc 1 that people often struggle with a bit because there was this y and the y prime you have to put in. So what we do? Well, this is a product, and we have to take the derivative of the first, that is 3x squared, and copy the second, okay? And then we copy the first, and then we have to take the derivative of y to the fourth. But y is a function of x, so we have to think of this y as an inside function. So that is 4y cubed times y prime. This is why we needed to write the y prime here. This is from the chain rule, okay, that you get this. Okay, plus the derivative of cosine y, well, that is just cosine. The derivative of cosine is sine, so minus sine, so let me write minus sine y, but again, y is an inside function, so you get a y prime here. Plus, this is a product again. The derivative of the first factor is just 1 times ey, plus, and the derivative of the second factor, copy the first, take the derivative of the second, that is ey times y prime, because y is an inside function. So if I group the things with y prime and without y prime together, we would have, this would be the part without, and then the part with would be 4x cubed y cubed minus sine y, right, is that we're done with this term, and this term, plus x e y, y prime. And that is df dx. Now, also in implicit differentiation in that chapter, you might have seen also that it is sometimes a little bit, so when you do implicit differentiation, you kind of thinking of x and y as both variables, both functions. So you kind of making vague that you're doing away with x being the independent variable, y being dependent on x. You're making it symmetrical in x and y. And to do the best way to do that is actually write df is 3x squared y4 plus ey. So this would be here a dx then, right? We had y prime is also, this would be also dy dx, right? This is dy dx. So we multiply, so to speak, everything with dx, plus 4x cubed y cubed minus sine y plus x e y dy. Okay, so this way it is a bit, it is really symmetrical now if you write it this way. Okay, so that is df. Okay, so now f was just an expression. Okay, and then we say that if we take the differential of the derivative, the total derivative, sometimes people call this, then this is this given by implicit differentiation that way. And therefore, if f would be equal to a constant, this was just an expression, right? But if I put it now equal to a constant, what would happen then? If I take d of f of a constant is 0, right? So in other words, if this f here is a solution to this equation equal to 0, and this is a partial differential equation. Okay, so keep that in mind. But now I need to introduce something that you have not seen yet, and well, you have seen it, but you have not given a name to it. And this is something that is normally from Calc 3. So those that have taken Calc 3 will probably recognize this right away. This is the notion of partial derivative. There are several different notations for it, but I'm going to take a notation f superscript x. And what does that mean now? So partial derivative means take derivative with respect to x, but treating y as a constant now. So almost the opposite of what we did in the chain rule, in the implicit differentiation, where we say y is a function of x, so it's an inside function. Now we do take it as if it doesn't is a constant. So what does that mean here? If I take the derivative of this guy here, that means this is just a constant. So I can copy that and I only have to do this one. So the result would be 3x squared y to the fourth. Just copying the constant, but since it's the y, I keep it writing in the back. What about the next term, cosine y? What's the derivative of that? Pause the video if you want to think about it, but y is a constant. And so cosine y is a constant. The derivative of that is 0. Plus, and then x ey. Ey is a constant, only x, and the derivative of x is 1. So we get ey. Okay? So that is of, or f of x, the partial derivative with respect, so this is the partial derivative with respect to x. Okay, let's do the same thing for y now, because it's very symmetrical. So what is this? What is going to happen here? I'm not writing it down. I'm going to take the derivative with respect to y, thinking of x as a constant. So y and x are now two variables, and they are not related to each other when we do these partial derivatives. At the end, we're going to put them together, but now we treat them each separately. That's how you have to think of it. For the moment, we're taking them separately and think of them as unrelated. Okay, so if I take the derivative of this expression with respect to y, now x cubed will be the constant, so I get 4x cubed y to the third, right? The derivative of, where is it here? The derivative of y to the fourth is 4y cubed, right? That is why this 4y cubed comes. And where the x cubed form comes, that's just a constant. The derivative of cosine is minus sine. Y prime? No. We take derivative with respect to y, and that's the end of it. Y is the variable here. There's no y is not an inside function. Y is the variable. How much less of an inside function can you be if you're a variable, right? And then here, what is the derivative here? X is the constant, so we just copy that. Derivative of ey is just ey. Again, no y prime. Okay, so that is the partial derivative with respect to y. Okay. So, where are we? I kind of recognize these things. Let's see what this one, for instance. But that's exactly this part, right? It's exactly the same. And what about the other one? I hope you see it right away too, right? This one is exactly this one. So let's rewrite now what we did. That d of f is just the partial derivative of x dx plus partial derivative y dy. Sorry, this is an x and this is a y. I should be a little bit careful here. So you knew partial derivatives, because when you're doing implicit differentiation, that was basically what you're calculating. And in some sense, partial derivatives is way easier. You don't have to think about what is the inside function here. No, it's just y is just a variable, so just treat it as a variable, and x is then the constant. Okay. So, now, go back to what I was saying. I said, if you suppose you would have a differential equation, this differential equation equal to 0, then what I showed is that if f is a constant, if this f is an expression, right? So it's not an equation. If I put this equal to 0 or equal to any constant, then I would get an expression, get an equation. Right? If an expression is an expression, that's not a function. But if I put this equal to something else, to 0, or in this case I'm going to put it equal to c, so f equals c, by that I make an equation so that we have an implicit equation that defines y in terms of x. So far we have been treating x and y as separate, but once we put them equal to constant, we put a relationship between them and they become dependent upon each other. And in the optimal case, you could actually solve for y and you would have an explicit. We will see examples of that. Okay, so in repeating, if you would have this differential equation, then the solution is this equal to a constant. Okay, but okay, that is kind of cheating because we started from a function and then we said, okay, that's the solution to this differential equation. That's basically what we said. Sure, but now we're looking therefore for differential equations. So what is an exact equation? And now I can finally tell you what an exact equation looks like. An exact equation, let me see that I keep the same notation as in the book. Okay, so an exact notation equation is something where an expression in x and y, dx, plus n times x and y, dy equals 0. Here we have the dx and dy's instead of a y prime, right? So this is of course equivalent to this equation, right? And then hopefully you see now this is a linear first, not linear, this is a first order differential equation, okay? But this is the better form, because this is the form that it's already of, it's already of this type, right? Okay, so we have this guy and this guy. Now remember, what were these guys? This was the partial with respect to x, this was the partial with respect to y. So if we, in other words, if we have a function f, so that this is a partial with respect to x, and this is the partial with respect to y of this function, then this is the solution of this, then f equals a constant is a solution. Okay? Okay, so write me that down. If f of x is m, and f of y is n, then f equals a constant is a solution to this equation. And this is where everything, what we want to do now. But how do I know that there is such an f, right? If I am giving you a differential equation, let me give you one. Suppose we have the differential equation 3x squared y dx plus 4x cubed dy equals 0. Suppose that is a differential equation. That's a differential of this form, right? This would be the m, and this would be the n. So I'm saying if I can find the function f, so that if you take the f is an if I find an expression in x and y, if I take the partial derivative with respect to x, I get this. If I take the partial derivative with respect to y, I get that. I'm golden. I have a solution, namely f equals, not just f equals 0, but f equals a constant. Why a constant? Because remember, if this equation comes from taking d of f, the derivative of f, if you want. And of course, if you take if f equals a constant, then the derivative of a constant is 0. So that's why you get the 0 on this side here. Okay? Sure. Now, let's hope that this is the case. Okay? So let's. I want to find f. So in search of f. So what the condition was, remember, that the partial derivative of x should be this m. Sorry, let me be a bit. That should be this m, that should be 3x squared y. Okay, so what would f then be? Well, let's do the undo partial derivative with respect to f. So we're going to now take the partial antiderivative with respect to f. And what does that mean? It's exactly the partial, it's the same principle. We antiderive with x as the variable. This means that y is considered constant, or treated as a constant. So what does that mean if I antiderive here? So 3y, that's on its own is a constant, and I have to just antiderive x squared, which is x cubed over 3. So the 3's cancel, of course, plus a constant, of course, right? In general, if you antiderive, you have a constant here. Now, this is a part. This is a constant, but y is also a constant. So in principle, the c could depend on y. When we start thinking of y no longer as a constant, then the c might be depending on y. So this is what we're going to write as phi y. So this is a constant with respect to x, because that's the variable that we were integrating with. And that's what you do, right? When you antiderive, you do the antiderivative plus a constant. But what does constant mean? Something that does not depend on the variable. But we have two variables here, x and y. So the best we can say is that this extra constant here does not depend on x, but it still could depend on y. So we have to write Vy there. Now, why do we do this? Well, is this the solution? Well, yes and no, because we don't know what phi is. So now we need to find phi. Okay, how we do that? Well, remember this is the second part, right? F of x was m, f of y, the partial derivative with respect to y, should be this guy. We haven't used that yet. Okay, so we're using that f of y should be equal to 4x cubed. Okay, so that's the condition. This is the second condition. So this is the first condition, condition 1. And this is condition 2. Meaning I'm referring here to these conditions here. Okay? Okay, but I know I have a form for f, right? I have here, let me write f here a little bit. Here we had that f was x cubed y plus phi y. But phi was still a function that we need to determine. So we can calculate f of y. Partial derivative with respect to y. What is that? Well, x cubed is now, when you do the partial derivative with y, x cubed is a constant, and then the derivative of y is just y. Okay? Plus, what's the derivative of f phi? I don't know. But if you don't know, that's what mathematicians said, and you write just phi prime. Okay. Oh, okay, but sorry, sorry, let me see here. 3x squared y, 4x cubed. Oh, I'm sorry, I copied the wrong one. Sorry. This was supposed to be... No, there should be no 4 here. I'm sorry, I copied this wrong. There's no 4 here. X cubed. Sorry, so this was supposed to be... I'm sorry, it was the wrong... This was the right thing, x cubed. Okay, 3x, this was, sorry, that's the one that you need an x cubed here. Okay, so now we put these two together, right? We said this should be equal to that, so we get x cubed plus phi prime is x cubed. So this says that phi prime is equal to 0. And this is something that we need to happen. Remember, phi only depended on y, so all the x's have to cancel. We'll do more examples where you see this happening. Now, what does that mean? Well, this just means that phi is a constant, right? Remember, phi is a function of y. So you have to antiderive this with y. In general, we get something here. I'll do another example where you get a real function here. This, we were lucky here, the function was just 0, but that means that the antiderivative is just a constant. Now, remember, what I'm looking for is a function f that satisfies this thing, and then any function of the form f equal to constant is a solution. So I need only one function, so I can take this equal to 0. I can this constant to be 0 here. This is now the final constant of integration, and I can choose this, I can take this to be 0. So my conclusion is that f equals yx cubed, or x cubed y, it's better perhaps write it in this order, x cubed y, f is x cubed y. That is this f, if f is equal to the form x cubed of y, then it satisfies these two conditions. The two conditions are met. You can easily verify this, right? So, x cubed y equals a constant is a solution of the differential equation. Remember, that's what this said, right? If you find an f that satisfies this, then f equals c is a solution. That's what we argued. Okay, so let me do this on another example, and then hopefully, well, yes, now, one more very important thing that I have to say. Sorry, I have to say this first. Does this always work? No. If I just take arbitrary m and n, it won't work. Because notice what was happening here, and I told you this needs to happen, is these x's, there are x's here, right? And these x's have to cancel, because this should only depend on y. This is phi depends only on y, so phi prime should only depend on y. So there can be no x's involved. So everything that has an x in there has to cancel. Now, I admit that this was a little bit simple example, so you don't see really what happens. Hopefully you see. Keep that in mind. In general, there will be y's, but the x's have to be cancelled. Now, That will not happen in general. That's special, very special that these things cancel, right? So when does it cancel? Okay. So the condition is, so be careful. So this is an exact equation. No, let me write it up here. I have here. Is exact if, so this is something I haven't said what it is, right? The example I gave you satisfies it, but in general, what is the condition? If you take m, this m here, and now you take, this is the part that stands with dx, but let's take the partial derivative with respect to y, and do the same with n, but now with respect to x, then these two have to be equal. So an equation of this form is exact if the partial derivative with respect to y for the expression that is in front of x. So what does that mean? We would have to take the derivative here of with respect to y. Okay, so let's see what this is, right? So we have, this is our m. So what is my here? That is 3x squared. Partial derivative with respect to y means you treat x as constant. Okay. Then this is n, and so what is n of x here? Let's see whether that's not correct. Now we have to take derivative with respect to x, there's nothing else, so that is just 3x squared. And indeed, they are equal. So that the condition that I said has to be satisfied is satisfied, and it turns out that is enough. Now, for those that are curious, I mean, the textbook has much more explains than that, so you let you figure out these things yourself. You can read it yourself if you want more, but I just want to say, where does this condition come from? Remember, we are looking for a function, this function, so that this f here, that the partial with respect to x is m, the partial with respect to y is n. What does this then say? Suppose this is true, what does this then become? Let's look at this equation and write it in red here. So m is f of x, so it's fx y. What is n? N is f of y, so this would be f of y, and then you take partial x. So let's read what it says. It says that you take the partial with respect to x, and then you take this partial with respect to y. And what do you do here? It's just the order. First you take the partial with respect to y, then the partial with respect to x. But since y and x are, each time you take partials, one is considered a variable and the other one is constant, it doesn't really matter in which order you do this. So this is always equal. The order in which you do partial derivatives, that's the big thing from Calc 2, is doesn't matter. Right? So partial derivatives, what they say is commute. And that is exactly this condition. Okay, so, but all that is perhaps a little bit background where this comes from. Let's now put this really in practice. So practically. So what do we do? So I'll take an example here. So let's solve the equation 4x cubed y cubed plus 3x squared dx plus 3x to the fourth. Let me see, is this a good example? Yes. 3x to the fourth y squared plus 6y squared dy equals 0. This is the special form that exact equations are written in. Now, of course, a problem will be in general if you have to deal with many different types of equations to recognize the exact ones. And that's not obvious at all. But let's not concern ourselves with that. So this would be so what is the condition? Exact. So step 1. If we're going to pretend that this is the method for exact equations, we better check whether it is exact. Now remember what this means. This means that you take the expression in front of dx and take the partial with respect to y. So let me write it up here. So 4x cubed y cubed plus 3x squared with respect to y. Now what is that? That is, so meaning, these are all constants. So the only thing that happens in the derivative part is this part, right? What about the next one? Well, that is just 0 because it doesn't depend on y. Okay. Now, that's what we did here was take the partial derivative of the part that stands with the x variables, the dx, with respect to y. Now we have to switch. So we take this one, 3x to the fourth y squared plus 6y squared, and I have to take the derivative now with respect to x, the partial with respect to x. So now we treat y squared as constant, and we only have to take the derivative of x cubed, of x to the fourth, which is 4x cubed. And what is the derivative of 6y squared then? I'll let you think about it. You might be still thinking of implicit differentiation, also it is 12y times y prime. No, y is a constant as far as x is concerned in partial derivative, so it is 0. Now the condition is, is mx equal to ny. So that is the big question. That's what the exactness means. Well, yes, they are equal. You see these two expressions are equal. So once we know this, now we can say, oh, okay, so I know now that this will be f of some f, the partial of some f with respect to x. It's confusing, right? When we check exactness, we have to switch the variables. This part we take the y, and this part and this one we take the x, and we have to check they are the same. When we solving, we're saying this is a certain. We know that there should be a function f, so that if I take the partial derivative of that function, I get that. So what we need to do is now the partial antiderivative with respect to x. Of what? Of this one. 4x cubed y cubed plus 3x squared. And I'm going to just write it dx. But I have to keep in mind here this. So if you would show this to somebody in Calc 2, he would probably do the same thing, but he would make a mixed mistake because y is a function of x in general. But when we do partial antiderivative, it isn't. Okay? So this is really, so let's do it like split it up, right? The sum of integrals is the integral of sum, and then this is 4y cubed. That's all a constant, so I can bring this out. X cubed dx plus the antiderivative of 3x squared, or I can bring the 3 out, but let's not do that. Okay? So that is what it really is, right? So, but let's not do that. Let's do the whole thing at once, right? Okay. So antideriving this, taking the antiderivative of 4x cubed, just on x, that is x to the fourth, and y cubed is just a constant. Plus the antiderivative of 3x squared is x cubed. Okay, there's no y, so there's no confusing here. Plus, and this is now important, here comes a function that only depends on y, because we are doing partial derivative with respect to x, so this is a constant with respect to x. But it depends therefore on y still, because in general everything depends on x and y. But if it's constant with respect to x, it means it only depends on y. Okay, so that's the first part. The second part we need to do now is, we also know that this is our f now. This is going to be our f, and what we know is that this is going to be f of y. Right? We started from this, we found f by saying it is the partial of f is this. But we also know that the partial of y, of f with respect to y, is this. So we haven't used that yet, so we're going to use that now. So we use that 3x to the fourth y squared plus 6x squared, no, 6y squared. 6y squared, there's a glare in my, okay, now I see it. 6y squared, that is f of y, right? That is f of y. This is just writing down what I said there, but I know what f of y is now. I take the partial with respect to y of this function. So now now y is the variable, so x to the fourth is just a constant, so I get x to the fourth 3y squared. The derivative there, what is the derivative of x cubed? 0, because I'm taking derivatives with respect to y. So that is 0. What is the derivative of phi with respect to y? I don't know. Well, if you don't know, write phi prime. Good. So let's see what we have now. We have this equality. Okay, the fy in the middle, let's get rid of that. That was just to help us to get to the equality. And what I said, what I promised is, if the equation is exact, so if this is true, then all the terms with x are going to cancel, and this is exactly what happens. So what we're left with is that phi prime is equal to 6y squared. Oh, but then I know what phi is. Phi is a function of y, right? So I have to antiderive with respect to y, so this is 6y squared dy, antideriving, that is 2y cubed. Okay? plus c, it's okay because we're looking only for one capital F. So conclusion, capital F is equal to x to the fourth. We have now everything, right? We know this part we already knew, but now also we know what phi is. Phi is 2y cubed. That is F, and so a solution, the general solution, and this is the general solution, it's also part of the theory that I'm not going to explain, but you just accept that, is putting this equal to a constant. X to the fourth y cubed plus x cubed plus 2y cubed equals a constant. That is our general solution of our differential equation. Now this is in implicit form. Okay, so this is the implicit form, and very often in this method, that's the best you can do. But in this case, it's rare, but in this case, you can actually do better. Namely, you see there's only, y only occurs as one in one occasion, namely as y cubed, right? So we could isolate that. So we see that y cubed is c minus x cubed over x to the fourth plus 2. And now I see that y is the cube root 2 plus x to the fourth of this expression. So we actually get an explicit. Is the explicit solution. And this is sometimes what you really want to see, this, the right explicit solution. I'm not saying this is always possible, but if you can, you should try. Okay? And you see these are kind of complicated functions already, right? It's right. You start from something that looks a little bit innocent, but yeah. So last thing I want to say is, this is only one way of doing it. Why? Because what did I do is, let's review what I did. I said, okay, quick review of what it needs to be done. They give you a differential equation, okay? You have to first check that it's exact, and that means that you take the partial derivative with respect to y, wait, what I wrote now? Oh, I messed up my M and N here. Sorry. Oh, Jesus. I'm so sorry, guys. I did it correctly here, right? That's what I said. So, sorry about that. I did, what is M and N? Or did I said it correctly here. So sometimes it's, see, this is the problem with formulas. Formulas throw you off. It's better to just memorize what you need to do. What I need to do is you take this, the expression in front of dx, and take the partial with respect to y, do the same here, but now with respect to x, and compare that these two are the same. So that's the first thing. That is checking exactness. If you have exactness, then you say, okay, I know that the thing that is in front of the x is a partial derivative of some function f. And how do I find this function f? Well, I just do partial antiderivative with respect to x. That gives me an expression that still has a constant that might depend on y, and which I don't know. To determine that constant, I now look at the second condition, namely that this one is the partial derivative of f with respect to y. So I'll write that up. I have my f, write down what that means, and put them equal. A lot of things cancel, and I can solve for phi. I get phi prime, and I can find what phi is, and I'm done. That's the method. But why did I start with saying this is the partial derivative, this is the partial derivative of f? But it's also true that this is the partial derivative of y, so why didn't I start with this one first? You can do that, and the calculation will be slightly different, the answer at the end will be the same. So you have a bit of freedom here, whether you start from here or you start from here. Let me not work out in this example, it's done in the textbook, but I'll do it in the next example, where it becomes actually kind of critical. So it is a bit ugly here, so bear with me. So the equation, it is an example of the book. Okay. Y exy tangent x, I know, don't scream, don't yell, don't run away. Exy secant square x dx plus x exy tangent x dy equals 0. Okay. Step 1. Is this actually exact? So what do we need to do? We need to take the partial with respect to f, partial with respect to the other variable, with respect to y. Sorry, I said f, I don't know what I said here. Here we have to take the partial with respect to x. You have to really, we're switching x and y left and right, right? So we really pay attention to the various steps and which variables are involved here. So let's do this. The partial with respect to y. So this is a product. Tangent x is a constant as far as y is concerned. So we have the derivative, this is still a product though. This is a y here and a y there. So this is a product. So we get the derivative of the first term, that is 1, copy the second, exy tangent x, plus, now copy the first and take the derivative of exy. Now be careful, what is that? The derivative of e is exy. But xy is now an x inside function and I have to take the derivative of that, and x is a constant, so this x comes out here. Okay, this from the chain rule, this x comes from the chain rule applied to this here. Now x is a constant as far as y is concerned, but it still comes out there, right? If this would be e to the 5y, you have to have 5 here. So it's e to the xy, so you have to have x here. Okay, and then the tangent x is again a constant that I have to copy. Plus, now I do the same thing here. That is e x y x, for the same reason again that we have this x here, and the secant square is just a constant. Okay, that's the respect to x. What is this here? Let's write this on this side. Now with respect to x, okay, that's a product again. So the derivative of the first one is 1, and then copy the rest. Plus, now the second, so copy the first, take the derivative of the second, that is exy. Now what do we get here? X is the variable, y is the constant. If I take the derivative of exy, that is exy times the derivative of the inside function, that is y, because that's a constant. Okay? Tangent x. But tangent itself is also a function of x, so we actually have the triple product rule here. So we have copied the first two, and now take the derivative of the last one, which is secant square. And now we match. Is this the same? Let's see. This term is the same as this term, and this term is the same as this term, and then this term is the same as this term. So yes, they match. Okay. So what does this mean? So now I have so I know that this is what. Let's write down this is. We know that this then there is an f, so that this is the partial of f with respect to x now, and this is the partial with respect to y. And so what we need to do is to find f. We have to antiderive this with respect to x. Professor, that is not something I want to do. Look at that. This is probably not possible. And you're right, this is probably not possible. Well, yeah, there is something called partial integration that you could perhaps, integration by parts, very, very difficult. I'm not sure that it works or not. So what now? Well, we had a second option. We could also start from here and say, okay, in order to find f, we have to antiderive this with respect to y. First you thought that's not good, but then you're thinking, well, x and tangent x are just constants. So it is really exy, and x is also just constant. It's really just, okay, I want to do that. Okay, so f is the antiderivative with respect to y of x exy tangent x dy. So meaning here, so this is the partial antiderivative, right? Partial antiderivative with respect to y. The notation, unfortunately, is not, I don't want to introduce this complicated notation where you would better see this, but we know this. So just keep that in mind, that's what it is. So that means that x tangent x is all constants, and I just have to antiderive this. Oh, and the antiderivative of an exponential function is actually easy. That is just an exponential function. But wait a sec. If I take the derivative of exy, because x is a constant with respect to y, when I take derivative, it comes out. So I have to compensate by it. Right? So, and the deriving 5t dt, that is e5t divided by 5. The divided by 5 is because if you take derivative of e5t by the chain rule, there will be an extra 5, and you want to cancel that. It's a compensation rule. And here, instead of 5, there's an x. That's the only difference. But it's a constant for y. Oh, is this a constant for y? So plus a constant, then what should I write here? Let's think about that. It's a constant with respect to y, but that means that it still might depend on x. So we should write it as phi x or psi x. In the book they use a different letter, but let's just write phi. Okay, first of all, these x's cancel. So we see that f is of the form tangent x exy plus phi x. The next part step in this procedure is, remember, we did the partial and the derivative with respect to y. In other words, we used this information. But we also still need to know the other information, right? So we need to write down that this whole long spiel here, where is it? Y exy tangent x plus exy secant square x. Let me see, I copied it. Here, tangent x. Yeah, that is the partial of x of f with x, and so the partial of f with x, I can calculate that here. That's the product rule here. That is secant square. That's the derivative of tangent x, right? Copy the second term, plus copy the first term, and now take the derivative of the second term. That is exy y. Why is it y there? X is the variable, y is considered a constant by the chain rule that comes out. Plus, well, now we have the derivative of phi here, that is phi prime, with respect to x, right? What should cancel now? Well, now f depends only on x, so everything that has a y in it should cancel. Let's hope that this is the case. Well, this one here, y exy tangent x. Oh, okay, that's gone. Oh, okay, this one is also gone. What am I left with is, in this case we are lucky again, 0 is phi prime. This means that phi is an actual constant, but we can take it, so take phi equal to 0. Remember, we only have to find a solution to this equation, and 0 is a solution. So, conclusion, f is actually equal to tangent x exy plus 0, but we don't need the 0 here. And therefore, the solution of the exact equation is c equals tangent x exy. And again, if we want to, you can make it explicit, right? Let's try to do this. Xy, tangent there. Now I want to get to the exponent, so I have to take ln of both sides. So this is ln c tangent x equals xy. So y is equal to 1 over x ln c over tangent x. Cotangent x if you want. Okay, so that is our general solution. Okay, so you see here, it's essential that we had both options, because if we had to deal with the only option, if we would have to enter derivatives with x, we would not be able to do that. Okay, all right, so this is something you have to practice a lot, and also we'll do homeworks on this, and we will then also review, because there will be a quiz on this thing as well. Okay.